All right. So yeah, more titrations. I wanted to do another full length, from beginning to end titration problem like last time. Um, Last time it was tricky. This was on Sunday. Um, it took us about an hour to get through one of these because it takes a lot of explaining, and these are, multi-step problems. But I want to make sure, like, the thing I really want to nail down today is knowing what the process is. Like, I know you guys know how to do a BCA table. I know you know how to do an ice table. The tricky thing is seeing, like, when do we do which? And you know how to do Henderson-Hasselbalch. It's given to you in the formula sheet, but it's like there's certain tricks that can kind of clue you in on this is when I need to do Henderson versus this is when I need to, go from moles to molarity and do a whole ice table or something like that. Um, so in this instance, we got a titration of 35 mils of 0.25 molarity weak base, and it's being titrated with 0.145 molarity bromic acid. So as a little visual, because we don't want to get too lost in the writing, this is what we're talking about. This is a titration. I know you know it, but we have the weak base sitting in this flask, and we're slowly dripping in this strong acid, so the bromic acid. And there's a lot of different types of problems you can do with these. So I pulled out four problems with this one example. The first one's the easiest. I'm asking you to determine the pH before we add any of the bromic acid. And so somebody want to say like what their thought process is on how to solve for pH when we haven't even done anything. We haven't added any titrate. What would that look like? Yeah, mix it with water, and that would be forming what kind of table? Ice table, exactly. Yeah, so we don't have anything to react. So we aren't doing a BCA table. When you're doing a BCA table, you're talking about two things reacting, and we're not doing anything with that yet. So we're only doing an equilibrium ice table. Okay, so yeah, this is what we've been doing for almost a month now. So no surprises here. We're taking the weak base. You can write a weak base as B minus. That's how we sometimes notate that. Plus water goes to form HB. So this is the conjugate acid that we're forming, and hydroxide ions. So that's what we are really concerned about. And again, we're doing the KB equals the equilibrium constant expression. We can get rid of this minus X down here again because we have a small K value. And real quick, let's see what that gets us. We get an X value of 2.12 times 10 to the negative 3. And we know that if we take the negative log of X, since that's our concentration of hydroxide, we can get a POH. Let's do that. And the POH is, I got 2.67, there we go. And 14 minus that is 11.33 as the pH. So we're good with that, right? Nothing weird. And also let's do a quick, reset. Does that value make sense? A pH of 11.33, it should, because all that we have so far is a weak base. So we want it to be at least on the basic side of the pH scale, so above 7. Now we're going to get into the titration stuff. And this one, I'm throwing you straight into it. So again, I talked about this past session. Has he ever thrown the term halfway point at you guys? Was that in the active the other day? Once or twice. Once or twice. Okay, so that's fair game for a test. So we'll talk about that. The halfway point, this is a vocab term that would be good to memorize. Does anyone know what the halfway point is? Yeah. When half the acid is usually done. Exactly. It's really simple. So if we This one we are going to do a BCA table. I'll let you know that. Or at least we need to go to moles. And we know that when we go to moles, we're going to be reacting it away the more bromic acid we add. So if we've added enough bromic acid to get to exactly half of the starting moles of that weak base, that's the halfway point. And so this problem is a problem that you could see on the test. It's not asking for a pH. So this one is asking for a volume, and we're asked to find the volume of bromic acid it would take to get to the halfway point. So this one you kind of have to do a few steps, and it's a tricky one. So see if you can spend a minute or two working on it. If you have no idea where to start, don't worry, I'll go over it up here. But think about what we'd have to add to remove half of those weak base moles. And then once we have a mole value, think about what we could use, and I'll give a hint, what we could use here to go from moles to liters. That's going to be the trick. So I said you had to do a BCA table. That was kind of a lie. You don't need to do a BCA table, but it helps in my mind with setting this type of problem up. The reason we don't need to do a BCA table is because we're not finding pH, but I'll kind of show what I'm talking about here. So, first things first, we know that we're reacting something away. So we have to go from moles to liter, or molarity to moles. So we're taking the molarity of our weak base, multiplying it by that volume of 35 milliliters, and we get 0.00875 moles of our weak base. That should be good. Now, again, we said the halfway point is once we've reacted half of that away. So I'm going to take that value in moles and divide it by 2. Nothing bad about that. And if we think about this from a BCA standpoint, if we need to get to this many moles of our weak base, how many moles of bromic acid do we have to add? We know that every mole we add of bromic acid, we're subtracting away from this value. So if we added this same value in moles of our bromic acid, wouldn't that get us to the halfway point? Does that make sense? So I'll write it out as a BCA table because helps my brain kind of think of it. Again, we have that weak base plus the strong acid. So I'm going to represent that with an H plus going to form the conjugate acid. And we know that we're starting with 0.00875 moles of our weak base. Now, if we added 0.00438 moles of our bromic acid, that's what's subtracted over here, leaving us with no more moles of the strong acid, but the exact halfway value in moles. And we'd also be adding that over here, but we don't really care about that for this problem. So this is the amount of moles we had to add of our bromic acid, and now we need to find the volume that would take for us to get this many moles. Does anyone have an idea how we can get a volume? Yep, we use the molarity because the molarity is a unit conversion in and of itself, right? Because it's moles per liter. So if we took that 0.00438 moles of our strong acid HBr, and we flipped molarity upside down, so liters would be in the numerator. That's going to look like 1 liter per 0.145 moles of the bromic acid. Again, this is the molarity that's given to us in the problem. And that gets us our answer. So 0.00438 divided by 0.145 is 0.030 um, liters. And so, in other words, that's 30 milliliters. So on a test, you would probably ask it for the answer in units of milliliters, and that would be our answer. Yeah, that's the definition of the halfway point. Yeah. And let's do some other conceptual stuff that this is like going deep into. This is probably the furthest you would ever push a conceptual problem on titrations, but we see that at the halfway point, and this is an important thing to know for titrations. We have 0.00438 here, and then we have the same value over here for our conjugate acid. Do you remember him saying anything about that in terms of Henderson-Hasselbalch? When you have an equal amount of the buffer? Yeah, so if we exactly. So Henderson-Hasselbalch is pH equals pKa plus log, again, of base over acid. And if base and acid are the same quantity, it's 1 over 1. Log of 1, like you said, is 0. So we can say that at the halfway point, pH equals pKa. So if he also asked you, this would be actually a really easy problem. If he said, what's the pH at the halfway point? All you got to do is take that Kb, turn it to a Ka, and go from Ka to pKa. And that would be your pH. Does that part make sense for everyone? Cool. If any of this is confusing, I'm happy to talk more about it. But let's go to the next one. This is a problem where we're determining pH, and we're doing it at the equivalence point. Does somebody want to define what the equivalence point is? Yep. So if we said the halfway point is when we go from this value to half of it, the equivalence point is when we go from this value to 0 down here. So meaning we'd have to add the exact same moles of our weak base. We have to add that value in moles of our strong acid to get them both to 0. So spend a few minutes working on this one. This is a longer kind of problem. This problem has almost 3 steps that we need to do. It involves a BCA table, and as a hint, it's also going to involve an ice table, and I'll explain why. It's going to be after. Yeah. So anytime we're doing a titration, we're reacting to things. You always do the reaction first, and then if there's an ice table, it will come later. And reactions are BCA tables. Yeah.
Total volume be 95? 60 milliliters hydrochloric acid to neutralize it, and 35 units 30.
I'll have to do the math.
Or halfway point was 30, right?
Halfway point was, yeah, I guess that's a good way to, I think that works. Yeah.
Too simplistic.
I'll show you how I do it, and it's foolproof. That might honestly work, and we'll figure that out in a sec. But we have to use a similar process to that last one where we invert the molarity to find the volume unit. So you might be right about that. Not sure. All right, I'll start working on this one up here. If you're still going, feel free to keep working, but let's go through this. So this part right here shouldn't be too different from what you're expecting, right? We're starting with the BCA table, and we define the equivalence point as the time where we've reacted away all of that starting weak base, meaning we have to add this exact same number over here with our strong acid, right? Because it's going to subtract it down to zero, meaning we're also going to be left with zero of the strong acid. And the only thing we have left here is that conjugate acid. And the reason we can't do Henderson-Hasselbalch is what do we need for Henderson-Hasselbalch? We need both components of the buffer. Yep. So if we had a value here and here, we'd be good to do Henderson-Hasselbalch. But since this is zero and we only have one part of the buffer system, we know we need to go do an ice table. So the next step is this is in units of moles. We need to turn it into what? Molarity. Yeah. So BCA table, again, always moles. Ice tables always have to be molarity. So we can't go straight from this value and plugging it into our ice table. We have to do a middle step, and that's going to be finding the molarity. And we're going to do that over here. So we know the numerator is moles, so we already have that, but we need to find the total volume, right? Because it's moles over liters of the solution. So we've reacted away all of our starting weak base, so we know, if nothing else, there's at least 35 milliliters in here, right? But now we need to find out how many liters or milliliters of that bromic acid did we have to add. And we're going to use the same method we did up here, where we take the moles and invert molarity to get a volume. So I'll do that real quick. 0.00875 moles is what we added of our HBr, and then times 1 liter per 0.145 moles, because that's our molarity. Let's see what that gets us. That gets me 0.060. Yeah, so that method that we were saying kind of does work. 60 liters. So overall, we have 95 milliliters or 0.095 liters in the denominator here. So let's do that real quick. 0.00875 divided by 0.095 gets us a molarity value of 0.092. Great. So now this is what we're going to put into our ice table here. So we have 0.092. We don't care about water. 0 is roughly 0 minus x plus x plus x. And this is nothing new, right? Now, what are we going to use? Are we going to use Ka or Kb? Ka. So we're forming hydronium ions, meaning we're acting as an acid, right, in this ice table. So anytime you're forming hydronium ions, you need to use Ka. So the Kb given, we're going to do the Kw, Kb, Ka formula. That looks like this. Ka is Kw divided by Kb. I'm not going to write the whole thing out, but 1 times 10 to the negative 14 divided by 1.8 times 10 to the minus 5. We get 5.56 times 10 to minus 10 as our Ka. So that's what we're going to set equal to x squared over 0.092. And then, yeah, we don't want that minus x because it's small enough. I'm going to multiply this by 0.092. Take the square root. We get an x value of 7.15 times 10 to the minus 6. We're going to do the negative log of that. We get a pH of 5.15. So again, long problem. I don't think I mean, he could give you something like this on the test, but I think it'd be more likely he'd give you he'd break into a smaller step, like say, what is the molarity that goes into the ice table or something like that. But is there any step here? So again, we did this part kind of first, and then this part, and then the ice table last. Is there any part that you guys want me to go more over?
Only do an ice, like you only do an ice table after a BCA table if you don't have the acid base.
Yes.
Okay.
Yeah. if you have only one thing left over, basically. And so the best example of that is at the equivalence point. Because we're going to see in the next problem what happens if we added an excess of that strong acid. So what if we added something and we still had some H plus here, and then we also have the formed weak acid? Yeah.
But
Yeah.
if you have a strong base and a weak base, or a strong acid and weak acid, you can ignore the weaker one.
Yeah. Yeah. We're going to talk about that on this one. So that's exactly right. For this next one, we're going to have a little bit of this and some of this. This will literally do nothing to the pH. 100% of the pH is determined by this because it's too weak of an acid to affect that. Yeah. So we can try that. See if you can solve this one on your own. So what would happen if we added 120 mils of bromic acid? So again, we're adding new thing to the flask. So we have to do a BCA table, right? Because we're reacting things away and see what the pH would be after this. So here's the work for this one. Again, we're doing a BCA table. We go from molarity to moles. So we need to use that 0.12 liters that we're adding multiplied by that molarity. And BCA table is a really important factor is that when we're doing this C row, we always subtract the smaller value, right? So in this case, we're subtracting away all of the weak base, but we're still left over with some of that strong bromic acid afterwards. And what I was saying right before this is the weak acid that we formed doesn't matter. It's not going to have an effect on the pH. The pH is going to be fully decided by the strong acid because it's like an order of magnitude greater in terms of its strength. And so from there, if we can find the molarity of H plus, we can that's the concentration of hydronium ions, we can get the pH. So we have to take this mole value that we were left with here, divide it by the total new volume. So that's going to be the 0.035 milliliters of the weak base plus the 0.12 liters of the bromic acid. We get this value in molarity, negative log it, and we get 1.25, which should make sense, right? Because we're going above and beyond, we're adding excess of strong acid. So if we were to draw out this like titration curve, remember we said before we did anything, it was 11.3. Let's do this real quick. This is the pH over here. So this is like 14. This is 0. Can't let it be 0. We start around here at 11.3. We're slowly adding more. Maybe right here is where we're at the equivalence point, or the halfway point, sorry. And then we're going to hit the equivalence point right here. And then we see that right here is where we're past the equivalence point. And this is what we're saying is around 1.25. Does that part make sense? Cool. I should say volume of HBr added on the x-axis. Cool. Do we feel okay with titrations? There's a lot of practice on them. The other one, last pass worksheet or last pass video is recorded too. Kind of goes through these same steps, so there's a lot of practice if you guys need it. And then on the quiz review on Sunday, I'll probably do some more problems like this. Maybe not a whole entire one because I don't want to spend the entire time on it, but some more problems with like equivalence point and stuff like that. So now let's go into this new stuff that we learned yesterday. So this is the dissociation of these solid salts. So we talked about another K, KSP. Anyone want to say what the KSP stands for? What do we call that thing? It's the solubility product of constant. So that's what the SP means. And it basically represents the amount of aqueous ions that we're forming at a equilibrium with the salt. And we talked about saturation and supersaturation, I believe. Maybe that'll be in the recording for tomorrow. But honestly, I think KSP is not too bad. I think it's definitely easier than titration stuff. So we're going to go over it. Hopefully we can make this stuff click. But first, to get like really good review, going back to Chem 131, do a balanced dissociation equation for PbI2, so lead iodide. That's a solid salt that we could add to water. And you need to be able to do these dissociation equations to do these types of problems. Yep, see ya. Here's what I got. Right, we got lead iodide with a 2 as the subscript. So the 2 shows us that we need 2 of these iodine ions to balance 1 lead. And lead is like in in the metals in the middle. They kind of have different ionic charges depending on different stuff. So, we don't have a good clear rule based on the periodic table, but we can use this 2 to tell us how many or what its ionic charge is. So if we need 2 of them, and we know that I is going to be 1 minus, right? That means that this is Pb2 plus. And so then if we wrote out the KSP, and as a quick review, again, solids don't go into any K expression. So that's why it's only going to be this times this, and this is going to get a square of 2 from the coefficient. So now let's put this into practice. If I gave you the KSP value as 1.4 times 10 to the minus 8, I could ask you to find something called molar solubility. And that basically represents the concentration of this soluble ion in solution. And so see if you can do this based on what we talked about yesterday and what you did on the active, but I'm going to go over it up here too. We'll spend a couple minutes working on this one. Let's go through this. So I always write molar solubility as a capital S. I think that's how he was representing it as well. So if we think about from an ice table perspective, where you do the whole like plus X, minus X, whatever, we know that over here we would write this if this was like, I don't know, say ICE, we did that over here. This would get a plus X, and then this would get a plus 2X, right? X or S. So um, that's the same thing. So we're going to plug these into here. So it's going to end up being X here and 2X going inside the bracket. So it's really going to be X times 2X squared. And we know that this only goes to what's inside this parentheses. So it's going to be actually X times 4X squared, meaning it's really 4X cubed or 4S cubed. Same deal. And that's what we're setting equal to this KSP value. So 1.4 times 10 to the minus 8. And now all we have to do is solve for x. So divide by 4 and then take the cube root of it. And it's really that simple, solving these molar solubility ones. So S or X, will do S, I guess now. The molar solubility is 1.52 times 10 to the minus 3 molarity. Not bad, right? Cool. So now, next one, similar problem, similar type of problem, where again, we're giving you the KSP and I'm asking you to find the molar solubility. And then the last one we'll do after this is where I give you the molar solubility and we're going to ask to be asked to find the KSP. So that is basically the same thing, but in reverse. So I'll show you that in a second. Let's do this one first. Hopefully you guys remember your polyatomic ions, or at least phosphate. This is how you do this one. Again, this part, straight Chem 131. We're breaking up silver phosphate into its two separate ions. Phosphate is one of those polyatomic ions we got to know. It's PO4 with a 3 minus, and so Ag is going to be Ag plus. That's how we can figure that out. So it'll be three of them plus PO4 3 minus. So um, if you need to review with that, feel free to stay after or let me know right now. I can talk about it. But um, so again, if we were doing like an ice table type of thing, we know that we would add plus 3x here because there's a 3 as a coefficient and plus x here because there's only a 1. And so that is kind of how I think about these ones. If we set up the KSP expression, it's going to be Ag plus to the power of 3 times phosphate. And then these are the concentrations. So we can plug them straight into these brackets. So it'll be 3x cubed times x. What is 3 cubed? 27. Yeah. That is like, for some reason, my brain will always say 9. But don't make that mistake on the exam. 3 times 3 to the power of 3 is 27 x cubed times x still. Can't forget about this guy. So it's really KSP equals 27x to the power of 4. We said KSP is 1.8 times 10 to the minus, what is that, 18? Yeah, minus 18. So let's solve for x here. That's what you got. Okay, let's see. Yep. So the molar solubility, we call it S, 1.61 minus 5. Molar. Is that okay with everyone? Cool. Yeah, you can also maybe like if you do a few more of these, you might start to learn the trend where it's like you can get 4s cubed, you can get 27s to the fourth, or you can get 108s to the 5, depending on what the breakdown of these ions is. So you might not even need to do all this writing out if you want to be real quick with it, but I would still on the test. So if you, so yeah, if you had x, mhm, yeah, you could have 108 x to the fifth equals KSP is another option. So, all right, and now let's do the last one where you're solving for KSP by being given the molar solubility. This one's kind of like working backwards. So spend a few minutes. If you remember how to do this from class. Oh yeah, for sure. Um, yeah, yep. Yeah, here's the process for this one. Really the same method as those last two, but instead of having KSP and solving for S, we're going to set it up the same way, but now we're given S, so we're going to plug that in and solve for KSP. So again, 2S and S are going to be the like ice table equilibrium concentrations that we're going to plug into this KSP equation. We know we still need that 2 to be a exponent as well. So it'll be 2s squared times s, so 4s cubed. And then yeah, all we do is put in that KS or that molar solubility where s goes. Let's see what that gets us. Don't forget PEMDAS, all that stuff. And I got a KSP of 1.20 times 10 to the minus 12. And this is unitless because K is always unitless, right? Feel good about that stuff? Sweet, yeah. KSP, molar solubility, not too bad. And let's see, is that, what do you guys have before the end of your test? I guess you're finding out tomorrow.
We're gonna like, before class, we're gonna watch the video, that's gonna be like our lecture.